Hi everybody, so we're going to try and get through the problem sets. There are a couple that I actually want you to skip just because it's combining some energy and some transfer of energy and some momentum stuff, and I just don't think we need to worry about those. But this is pretty much 1 through 4, 1 through 4, I'm sorry, 1 through 4, and then 1 through 6 in the practice exercises. So we might as well get started. If we want to start with the first problem is about Tiger Woods. Hits a 0.05 kilogram golf ball, giving a speed of 75 meters per second. What impulse does he impart on the ball? And please don't pay attention to my typos, just because I was trying to get this done quickly. What impulse does he impart on the ball? So basically, we're going to live in this equation for the most part with these problems. F delta t equals m delta v, and remember the change in velocity is final minus initial equals change in velocity. So in this case, the final velocity is 75 meters per second. The initial, if it was a puck at, golf ball at rest, the initial velocity is 0, so the change in velocity is 75 minus 0, which is not 0, 75 meters per second. 75. So we're looking for the impulse. If you remember what impulse is, F delta t equals J. So we're actually looking for J equals m delta v. J, which is the impulse, equals mass of 0.05 times 75. Therefore, the impulse equals 0.05 times 75, 3.75 kilogram meters per second. Next, Wayne. We're talking about Wayne Gretzky, the great one, as it were. If Wayne hits a hockey puck this time, a stationary hockey puck, so again, the VI is going to be 0, the VF is going to be not 0. With a force that lasts for 0.01 seconds, makes the puck shoot across the ice at the speed of 20 meters per second, scoring a goal for the team. With what force does he hit the puck? So the final velocity here is going to be 20 meters per second. And this is, well, he's going to give it an impulse, J equals F delta t, which equals the change in velocity of the puck, and the mass of the puck doesn't change. So J equals F delta t. They give us the delta t. They're asking for the force. They give us the mass, and they give us the change in velocity. So we have to figure out the force. So F equals delta t, which is F times delta t, which is 0.01, equals the mass, 0.12, times the change in velocity, which is 20. 0.12 times 20 gives us 2.4, and the force times 0.01, we're going to have to divide by 0.01 on both sides. 2.4 divided by 0.01 should give us a force of 240 newtons. So there's that. Next. Tennis ball traveling at 10 meters per second is returned by Venus Williams. It leaves her racket with a speed of 36 meters per second in the opposite direction from which it came. What's the change in momentum of the tennis ball? And B, if the 0.06 kilogram ball is in contact with the racket for 0.02 of a second, what's the force? So this is a little trickier just because we're having a big change in velocity. The ball starts out by going this way at 10 meters per second, so let's make that positive 10 meters, and then she hits it and it goes that way with a velocity of 36 meters per second. So the change in velocity is going to be the final velocity minus the initial, and because this is going to the left, I'm going to say it's negative 36. So negative 36 minus 10, because final velocity minus initial velocity, that's going to equal negative 46 meters per second. So there is your change in velocity. What's the change in momentum of the tennis ball? Well, change in momentum, I guess, is going to equal m delta v, because whatever the velocity was in the beginning times the mass minus the change of, or the velocity at the end times the mass. You're basically going to get this equation, change in momentum equals the mass times the change in velocity. We know the mass of this thing is 0.0 0.06 kilograms, and the change in velocity is negative 46 meters per second kilograms. So in order to figure that out, 0.06 times negative 46 is going to be, the change of momentum is going to be negative 2.76 kilogram meters per second. For letter B, if the 0.6 kilogram ball is in contact with the racket for 0.02 seconds, what's the average force? So now we're going to use the equation F delta T equals M delta V. Well, this M delta V is the same as this M delta V, so we know that's negative 2.76. The force is what we're looking for, and we're looking for the change in time, which is 0.02 seconds. So we can just take that negative 2.76, divide it by negative point, not negative point, just 0.02, and we will end up with a force of negative 138 newtons. And that really just means that if this is going to be my great drawing of tennis racket, that means the tennis racket is applying a force of 138 newtons that way, which is why it's negative, because it's making the ball go that way. Next, I'm going to have you skip this one. Again, it's a collision one. It's a good problem, but we're giving you distances, and I don't think you should. I don't think it's fair for us to be looking at it. I think it's something that's more sort of AP level. We're going to be getting into two-dimensional kinematics and or two-dimensional momentum and collisions, and I think that this type of problem is just going to waste your time a little bit. So we're going to skip ahead to the Titanic question. On April 15, 1912, cruise liner Titanic sinks after running into an iceberg. What's the momentum for a 4.23 times 10 to the 8 kilogram ship running into an iceberg with a speed of 11.6 meters per second? So all I really care about is what the mass times, oh boy, stop, I don't know, stop, oh boy. I pushed a button on the stylus, and I shouldn't have. But we're asking what the momentum imparted is, and we now know that momentum is something that just gets transferred from one thing to the next. So P equals mv. We know the mass of the Titanic is 4.23 times 10 to the 8th times the velocity, 11.6 meters per second. So we're going to end up with a very, very large momentum transferred. 4.23 times 10 to the 8th times 11.6 is going to be really, really big. 49068 kilogram meters per second. I think that's right. And for what it's worth, if the captain had seen this thing even 1,000 meters before, there's so much momentum here. I don't care if you if you kick the engines into full reverse, just over 1,000 meters, that's not enough time to overcome this amount of momentum. So yeah, the best thing that they could have done is kind of turn the boat and try and glance off of the iceberg. Anyway, alright, so auto companies frequently test the safety of automobiles by putting them through crash tests to observe the integrity of the passenger compartment. If a 1,000 kilogram car is sent towards a cement wall with a speed of 14 meters per second, and the impact brings it to a stop in 0.08 seconds, what force brings it to a rest? So, again, M delta V equals F delta T, because we really aren't changing the mass of the car here. The mass is 1,000 kilograms, and from 14 to 0 is going to be a change in velocity of negative 14 meters per second, equals F, and the change in time is 0.08 seconds. So 14 So basically, to solve this, just divide both sides by 0.08. Go away. The force is going to be negative 14,000 negative 14,000 divided by 0.08, and that's going to be a very big force, negative 175,000 newtons. Rhonda, who has a mass of 60 kg, is riding in her car at 25 meters per second. This is why it's important to wear seatbelts. She slams on a brake to avoid hitting a dog. We get the time. What average force? So we're looking for the force again. We're going to live in this equation. F delta T equals M delta V. The force is what we're looking for. The change in time is 0.4 seconds. That is an eternity in a car crash. Times the mass, her mass is 60 kg, times the change in velocity, final minus initial, negative 25 meters per second. So 60 times negative 25 gives us negative 1500, and then we would divide both sides by 0.4. That is going to be a relatively comfortable negative, and again it's negative because the force is going backwards from where the car is going. The force is negative 3,750 newtons. Part B, if she had not been wearing a seatbelt and stops in 0.001 seconds, what's the force that we're dealing with now? Well, the mass times the change in velocity doesn't change, so we're still dealing with F times, well, we'll get to that in a second. The 60 times the negative 25 doesn't change. The time is what changes, so 0.001 seconds. Now you can see, if you know anything about this kind of math, to go with 0.4 in the denominator to 0.001 in the denominator, it's going to change things a little bit. 60 times negative 25 divided by 0.001, that is bone crushing. 1, 5, negative 0.0000 newtons. You walk away, you're carried away. Seatbelts save lives. How many times greater is the stopping force? Well, you can divide that negative big number, 1.5 million newtons divided by 3750. It's 400 times greater. ... Ouch. That is painful. Alright, next question. If 270 million people in the United States jump simultaneously, pushing off the Earth with an average force of 80 newtons for a time of 0.1 seconds, what happens to the Earth? F delta T equals M delta V. So we're looking for, I guess, the fact that the Earth is going to change its velocity slightly. The force you need to figure out, though. The force is not 80 newtons. The force is 270 million times 80 newtons. That's going to give us a big force. So 270, 1, 2, 3, 1, 2, 3, times 80 newtons. That is going to be, according to my calculator, 2.16 times 10 to the 10th newtons. Times the change in time. So there's my F. And this is going to be my delta T. And we said 0.1 seconds. Equals M delta V. Now the mass of the Earth, and we're going to solve for that. So I'll leave that there. The mass of the Earth, if I remember correctly, is 6 times 10 to the 24th kilograms. And they might have said in the problem it's 5.98, but just from what we did with planets and gravity, it's 6 times 10 to the 24th. It's an easier way to think about this. So I'm going to multiply this side times 0.1. So now I'm at 2.16 times 10 to the 9th. And then I got to divide both sides by 6 times 10 to the 24th. And if you use their If you use their mass of the Earth, you're going to come out with an answer that's about what I'm going to get. It's not going to be exactly what I'm going to get, but it'll be close. Your delta V is going to be whatever this is. So divided by 6 times 10 to the 24th. It's going to be a very, very small amount of change in velocity. Delta V is going to be 3.6 times 10 to the negative 16th meters per second. So essentially, this goes back to what I told you in the beginning of the year when the Prime Minister of China wanted his country. He was starting the world and he said, my whole country is going to jump up and throw the Earth off its axis. This is how much the Earth would slow down. And as you remember, anything that jumps up must come down. This would be just while everybody's in the air, and then the Earth would come back down. So it really wouldn't do anything to the Earth. Next question. This is actually what I really wanted us to sort of focus on, because now we're finally dealing with collisions. Sharkies. It's actually, this is funny, the guy who wrote this is actually from Massachusetts, so that's why you've seen problems from the Fleet Center with Paul Pierce. You've seen stuff in the Museum of Science. Sharkies is actually a pool hall in Worcester. I used to go there when I was your age. Anyway, Sharkies is, yeah. So in Sharkies, Maurice's place is waiting to take his last shot. He notices that the cue ball is lined up for a perfect head-on collision as shown, which you have the picture. Each of the balls has a mass of 0.8 kgs, and the cue ball comes to a complete stop upon making contact with the 8 ball. Suppose Maurice hits the cue ball. So we're going to get a force for a time that is going to give momentum to the cue. And that cue ball is going to then hit the 8 ball and give its momentum to the 8 ball. And that's where this is all going to come, because we're going to be able to use that momentum to get the velocities. So, the momentum of, the impulse, the force times time, we start out with 180 newtons times the time, which gives us the impulse, 0.005 seconds. So that is going to be, wish my phone didn't lock, 180 newtons times 0.005 seconds. That means that he's got an impulse of 0.9 kilogram meters per second. And that impulse goes into the cue ball. And that impulse becomes the momentum of the cue ball. So far, so good. So the cue ball rolls around, and then the cue ball hits the 8 ball and stops. So all of that 0.9 kilogram meters per second of momentum that he gave the cue ball now goes into the 8 ball. So the cue ball stops, and that momentum goes into the 8 ball. So if we know the momentum of the 8 ball is 0.9 kilogram meters per second, because that's what we gave it, that's what Maurice gave it, 0.9 kilogram meters per second equals momentum of the 8 ball, which equals just mass times velocity, right? mv. But wouldn't it be nice if they told us how massive the ball is, because we want the velocity? Oh, they told us what the mass of the ball is. So 0.9 kilogram meters per second equals 0.8 kilograms times the velocity of the 8 ball, which is what exactly we are going to be looking for. And on a really good day, we're going to divide both sides by 0.8. So 0.9 divided by 0.8 gives us a velocity of 1.125 meters per second. And that, my friends, is how to do that. And the next one, again, it's another one that's a dent, and don't worry about it. Just, I'm more excited about getting us to a point where we can have a car going this way and a car going that way, and then there's a crash, and then we figure out which way the car goes afterwards. So, hope this was good. Hope you learned something. Hope you did well on your homework. And I will see you in class as soon as I can figure out how to stop recording the screen. How do I stop figuring out how to record the screen?